the next one turns into 1, 6, 18, and 24, all the way down to the bottom. So what has happened? We started with a three-dimensional array and had to solve it. Now it's down to a two-dimensional array. All we have to do is solve that array, and we now have the solution to the tetrahedron with all the solutions. Okay, this is an area where I'm not good. I had to come up with a formula for this. And I struggled and struggled and struggled with that. But I did finally come up with something. Okay, and that was the formula down there. And again, you'll notice it's not an explicit formula. It's what's called a recursive formula. Now, explicit formula is like if you have you're doing the area of a circle, okay, and I told you the radius was 10, okay, you pop in 10 pi r squared, 10 squared times pi, you got the area, okay. With a recursive formula, you can't get the answer for a radius of 10 unless you know the answer for the radius with 9, for a recursive formula, excuse me. So you have to get the answer for a radius of 1, then 2, then 3, then 4, all the way up to 9. Once you have 9, then you can find the formula for 10. Okay, so it turns out I've got three formulas. I've got my multiplier array, which I've got an explicit formula for. And that was the one that, let's see. Okay. Explicit formula. I know what it is every single time. It's predetermined. The coefficient array, or the numeric array, explicit formula. I know what it is every single time. But for the D array, I don't. I've got that recursive formula that I came up with. But I said, okay, I'm going to put it together and try it, see what happens. And it worked. I came up with a conjecture. And here's what it was. I don't know why I have the plus sign there. This should be equals. If you take the product of those three arrays, the multiplier array, the numeric array, and the D array, it gave me the correct answer. Now, I was pretty pumped. So I sent it to OEIS for them to take a look at it. And I nervously waited. I knew that the formula worked up through 11. Okay, up to the solution rate, it worked every single time. I'm feeling pretty good. But who knows? Later on it might not work. Anyway, they sent it to this guy. And I'm not even sure how you say his name. Heinz, he's a computer science professor at Helpron University. And he took and was able to figure out, based on that information, he expanded it and went out to 40 solution arrays. Okay, huge. Now, again, he doesn't verify that I'm giving the exact results for the peaks and for the returns, but he did say, when he did triangle for the 40, that the numbers sum to the Catalan numbers. It summed to the Catalan numbers for 39 and 38 and 37 and 36. So in every instance, the sum of all of my formulas was always the Catalan numbers. It doesn't guarantee the formula's right, but it's one of those necessary conditions. So I was feeling pretty good about that. So I decided, well, this is part of this is what he turned in. And this is the number, these are the numbers he generated, except that you can't see this up here in the corner. This is page 5, 193. He turned down 193 pages of data on that. So he did a little check. And it got published, and this was the number for it right here. A253938. And so I'm saying, all right, I've got it. I'm going to go back to Map Overflow and put that on and see what they say about it. Well, I did. The person who put the problem on said, it's too complicated. You know, in a way he's right. The formula was very confusing, and I'm not sure complicated is the right word. I think confusing because there were so many steps. But this guy was able to figure it out. But, you know, it nagged at me, right? Because it's got to be something simple. This whole thing that it just didn't seem right, but there's got to be some way of simplifying it. And I thought about it for a year, and I didn't come up with anything. But nobody sent in anything contradicting what I said. So I went back on OEIS and typed it in one more time. And lo and behold, a guy named Arnold Alfred had my view. It was right there, waiting for me to discover. Now, he had just put it in back in 2005, but he had no use for it. He just thought it was a pretty sequence. Just lovely numbers, right? And how did he do it? Well, he combined Pascal's triangle with a sequence of factorials. In fact, the way you get it is this way. You put 1 factorial here, 1 factorial, 1 factorial, 1 factorial, 1 factorial, and then you put 2 factorial, 2 factorial, 2 factorial, 2 factorial, 2 factorial, 3 factorial, 3 factorial, 3 factorial, and 3 factorial. And the same pattern. He just thought it looked nice. And it yielded my theorem. Okay, but he had, a couple people had already put in explicit formulas for that. So I was able to take what the explicit formula for this, combine it with the 2 explicit formulas I had, and rework my formula. And so it came out this way. That's a lot nicer. You gotta like that. What we've got here is R, which is a number of returns, N, which is our semi-length, and down here P is for the peaks. An example of it here is putting the numbers in there with factorials 45. So there are 45 big paths with 4 peaks, 3 returns, and a semi-length of 7. And I checked with the previous results that I've got. So I posted that back on there. So this is what it ends up. This is my final conjecture right there. Earlier, I had you look at your table. For a length of 4, 2 peaks and 2 returns, this is how the formula works. And that's the answer you get, is 3. Now, the answer to the front page of the sheet I passed out to you is right there. 7, 3, and 2. It turns out there are 40 paths with that trait that there are 3 peaks and 2 returns. Now, note, this is a conjecture. It hasn't been proved. So, Conjectures usually stand for a little while, then somebody smart comes along, and I'll pick on my friend John, and they prove it, and it becomes the Spindler theorem. Okay? And he gets all the glory from proving it, type of thing. But it's out there for anybody right now to prove, and gain a little combinatoric fame. Now, I don't think that's worth much, but it's there for you to try. And that's it. Questions?
When did you start thinking about this particular?
You know, I've been working on semi-meanders for 20 years, and I just got bored, and I started working on this problem. And it only took me about 4 months to work on this one.
Really?
Yeah.
And how excited were you when you built your tetrahedron?
Oh, the tetrahedron was fun.
I just lit up when I saw it.
You know, what mathematician doesn't like to play with blocks? I mean, you know, it's and again, this is one of those problems that you can explain to anybody. You know, I'm not that great at calculus. If you ever try to explain calculus to somebody who doesn't know anything about math, they go wah 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 wah. You know, it just goes right over their head, right? But something like this, it's kind of nice because you can explain it to them and, oh, okay, I understand the problem. I'm not interested in it, but I understand the problem. So it's easy to explain the problem. But yeah, it was, you know, it was one of those things that it just came right. It was just had everything right for me. All my background and everything just happened to work for this problem. So got a little lucky. Lucky and a little stubbornness, I guess. So, hey, Nick.
So this formula is up on the OEIS now?
Yes, and it's okay, that's the location of it. It's got all the old stuff plus this new formula in it.
And are people adding any things to it, like noticing other connections to other problems with it yet?
No. Other than the one computer scientist, German computer scientist, no one's had comments to it. Though, anytime you put something up there, it goes through an editorial review. And anybody publish stuff in here, you go through editorial reviews, they are brutal. They just rip your stuff to shreds. They've never touched my numbers, but they always say, well, it would be better explained this way, or put spacing here, put a comma there. Drives you crazy. But I'll admit, when they were done, it was a better paper than when I started, so I'll give them credit for that. Okay, thank you. Oh, question, go.
Can I ask an unrelated personal question?
Okay.
Are you still a high
Wait a minute.
school? Are you still a high school teacher at Sandy or any high school?
No, I taught for 28 years at Sandy High School, and now the last 12 years have been at Tacoma Community College.
Oh,
So,
I was just wondering.
you see, you don't have to be in college to love mathematics, to be a math nerd. How many, Leslie Rice, okay, she was somebody who did some work. She was I don't want it to sound demeaning. She was a housewife, but she did some work that Roger Penrose, Dr. Roger Penrose, who was a great mathematician in England, praised her work because she had just come up with, she's working with shapes, tilings, and she did some fantastic work. So you don't have to have, PhD, DDD in mathematics to do original work.
Are there any applied fields where combinatorics is used? Not that it's not interesting in and of itself. Not that I'm familiar with it, but I don't know if it's put into computer science or engineering or
Yeah, actually,
mathematics treatment.
you know, the semi-meander one, the one I was talking about right at the beginning, and I probably won't be able to find it here. Oh, yeah, here. Okay. This one with loops, it has popped up in physics journals, and biology, combinatorics, and there's one other major field. So some of these things are over-related. But one of the things that happens is oftentimes, like with Alfred Arnold, the mathematics comes first and they find a use for it in another field. Other times you have a problem and then mathematics discovers a solution for it or discovers a pattern for it and formula for it. So there was once, where's Paul? Someday, who was it, the one speaker we had that say someday all mathematics will be found important, no matter how trivial it was? You don't remember.
I don't
Oh, you're
remember.
getting old. Jerry.
I just wanted to say that one of my favorite stories about math and the usefulness of math is that a number of years ago at MIT, there was a bunch of people, like when you get into those research fields, they get pretty far out there in the fringes, and they're so specialized that nobody else can talk to them except other specialists in their field. And so like at MIT at one point there was a bunch of researchers in math that had gotten way out in the fringes in their branch of mathematics, and there was a group of physicists that had also gotten way out into the fringes with the physics stuff, right? And the math people had gotten to this point where in their research they could not make any forward movement, like they'd been trying and trying and trying to solve some problem, and they were just feeling completely stuck, right? And it was very, very theoretical, and as far as anybody knew, there was no practical application of it, right? Same thing was happening over in the physics field, where a bunch of researchers were like way far out in the fringes and completely stuck. And both groups had been completely stuck, not knowing that the other group was stuck, right? For quite some time, and then all of a sudden, they started talking to each other over lunch or something like that, and started to realize, wow, that kind of sounds like something I'm sort of doing, but I don't know, right? Like I don't really know what you're talking about. And so they started sort of cross-pollinating, right? Some of the physicists started taking some of the math classes that were helping them be so specialized and vice versa. And all of a sudden, the math people realized that there was maybe an application for what they were doing. And once they had a physical application for what they were doing, they suddenly realized that's the solution to our problem. Like they had something physical to hang it on, and all of a sudden, they made this big giant breakthrough. And almost simultaneously, the same thing happened with the physicists because they had been stuck for so long, and they finally got far enough out in the fringes with the math to figure out that that is exactly the math they needed to get themselves unstuck, right? And so MIT, I think it was like within a year, 1 year period of time, both research groups were able to make huge advances because they finally, you know, the physicists had the language they needed to be able to make their advances, and the mathematicians had the physical construct that they needed to make advances. And so both fields sort of had like these huge leaps. And I've heard that that happens periodically, and it's happened on a number of times throughout math and science history, right? So.
I can believe that.
So all, like, I agree with you. I think that all of math will at some point be found to be useful.
I don't know. What,
It's Lobachowski. It's part of Lobachowski. You said what you said. It's actually on my syllabus.
Oh, okay.
There's no branch of mathematics, however abstract, which may not someday be applied to the phenomenon that we're
No, but there was one.
Branch.
Yeah.
Magic squares. We had a speaker once, a dead mathematician speaker, who talked about magic squares. Now, I don't know where that's ever going to be used, but maybe someday. Okay. I don't have an example of it, so I can't show it to you. That's it?
So in 2 weeks, right, Don Davis is sitting right here. He's going to give another net math presentation. Same place, same time?
Yeah. Right here.
What's the vague topic there?
Well, this is Raman Ujan, that Indian mathematician, who developed that proof that the sum of all the natural numbers, all of them, you add them all up, you know, you get a big number, right? His theory, you end up with minus 112. And so we'll be talking about that, and then trying to relate it. And I don't think it's a coincidence that abstract math and physical phenomena are connected, you know, you kind of wonder maybe it is the deepest source, the universe itself. I mean, there's some fundamental connection. I don't think that's just a coincidence. It happens so many times. Anyway, trying to relate that, but in a very non-technical way. There's no time to really get, not that I could get into the technical stuff, but there's no time to get into the technical. Anyway, that'll be the nature of the trying to relate that Ramanujan's, I'm not sure I'm pronouncing that right, but his Indian mathematician development or derivation of truth to some physical phenomena.
And just in terms of Don taught here full-time physics for 30 years.
You really learn the basics. When you do it for 30 years, you really get, at least you get the fundamentals really well. You know, you really do. I mean, I recommend it, really. If you really want to get the fundamentals, I recommend that.
Thanks again, Roger.
Yeah, okay.